Hello, so this is video number 1 of section 7.4, and this is a little bittersweet because this is the last section that we will cover in this course. So yeah, let's just jump right in. So what I want to talk about today, or in this video, is sort of a way we can analyze matrices that aren't diagonalizable. Before I do that, I want to briefly discuss some of the reasons we like diagonalizable matrices and just diagonal matrices in general. And then I want to introduce a decomposition of non-diagonalizable and even non-square matrices, which can allow us to analyze matrices in kind of a similar way. So, one reason we like diagonalizable matrices. Remember that if we think of this matrix A as a map from Rn to Rn by multiplication, and A is diagonalizable, I can perform this similarity transformation to map A, or to map each vector in Rn, to its coordinate representation under the spaces B, where the spaces B is defined by the columns of P in the similarity transformation. And then, remember, the diagonal matrix D similar to A is the matrix which, in a sense, is the matrix for the linear transformation that is the same as this one above, just represented under a different basis. And so what's nice about analyzing linear transformations using diagonal matrices is that we know exactly how much a diagonal matrix scales each of the entries of a particular vector. So as an example, notice here, you can see if I've got a diagonal matrix as the matrix for this linear transformation, we always know that the first entry is going to be multiplied by 2, and the second entry is always going to be multiplied by 3. And so sort of in a similar light, if A is an n by n symmetric matrix, then remember that the diagonal entries here on this matrix D are in fact the eigenvalues of A. And so here, if A is a symmetric matrix, you can actually show that the eigenvalues of A kind of measure how much each vector, or A stretches or shrinks any particular vector in any particular direction. And so we can do that using the eigenvalues of A and the fact that the eigenvectors of A form this orthogonal basis for A, or for Rn. And so using the length formula, right? So if I look at lambda, just any eigenvalue of A, and a unit eigenvector corresponding to lambda, then I can look at, well, I know the length of V is equal to 1, and the length of A times V is equal to the absolute value of lambda, right? So every vector in the direction of V will be scaled by lambda. And so doing this, if we ordered the eigenvectors, we could actually figure out sort of which direction is being scaled the most. So we like, again, diagonalizable and diagonal matrices. Easy to study the eigenvalues. We like symmetric matrices because it's very easy to study, when we look at them as linear transformations, how much A is stretching or shrinking each vector pointing in a certain direction. Right, so we want to know sort of if we've got this subspace or this shape in Rn, how is A changing that shape? But of course, like I mentioned, not every matrix is diagonalizable. And so what if we have a matrix that is not? So while we cannot always write a matrix as A equals P times D times P inverse, right? So that is to say, well, we cannot always diagonalize a matrix. For every matrix, we can write it in the following way. A equals Q times D times P inverse. And we'll discuss what these matrices are in a second, although the official definition for singular value decomposition will actually not quite use these matrices. But we can factor it sort of like this. And what we'll see is this is called a singular value decomposition. And so, called a singular value decomposition. And so this isn't the official definition. This is sort of just outlining what our goal for this section is. So our goal is to find a factorization of a matrix A, sort of like this. We'll see that this matrix won't always be diagonal, but it'll be almost diagonal looking. And then these two matrices, as we'll eventually see, will be orthogonal matrices. And so we'll get, kind of a nice decomposition, right? That, we won't get the same matrix, but it'll be similar to, how we diagonalize a matrix. So before we can do the singular value decomposition, we need to define what the singular values of a matrix are. So, before we officially define it, I kind of want to introduce some terminology before we define what the singular values are. So first, I want us to observe the fact that for any M by N matrix A, and so notice here in particular, we're not assuming A is a square matrix, that the matrix A transpose times A is symmetric. So we're making kind of a huge leap here with this claim, right? So I'm saying we can take any M by N matrix A. M and N don't have to equal, but if I multiply A on the left by its transpose, then I immediately get a symmetric matrix. So to see why this claim is true, if we represent A in this column notation, A1 through AN, then we can represent A transpose in this row notation, A1 transpose through AN transpose, right? So here all I'm stating is that the rows of A transpose are the same as the columns of A. And so then notice when I multiply A transpose times A, we want to keep track of what happens to each of the entries of this matrix as I compute this product. So notice that the 1-1 entry of this matrix is equal to, if I do the matrix multiplication dance, the dot product of A1 with itself, right? That I'm taking row 1, which is A1, matching it up with A1, and so this is A1 dot A1. Similarly, for this entry, I should get A1 dot A2. And so this pattern will continue all the way down the row, all the way down through A1.AN. But notice now, when I go down here to the second row of A transpose, This entry is going to be a2.a1, a2.a2. a2.an. But notice the dot product is commutative, so these two entries of the matrix are the same. And if I were to go all the way down here, I would get an.a1, an.an. And so notice, and so here the second entry of this row, just add it, would be an.a2, which is the same as the 2n entry up here. And so notice basically I'm filling this matrix A transpose A with dot products. And the dot products that reflect across the diagonal will always be the same because their corresponding indices will always be the same. So sure enough, A transpose A is a symmetric matrix. So this means we know a lot about the eigenvectors and the eigenvalues of A transpose A. So this means we can find an orthonormal basis, V1 through Vn. For Rn, consisting of the eigenvalues of A transpose A, lambda 1 through lambda n, where again V1 corresponds to lambda 1, V2 corresponds to lambda 2, and so on. So we can do something interesting now. If we compute the length of the matrix A times the eigenvector Vi, and so note here, this is not an eigenvector for A. This is an eigenvector for A transpose times A. But if we compute the length of this squared, we get the square root of AVI dot AVI squared, which, expanding the definition of the dot product, we get, and clearing the square root, we get AVI transpose times AVI. And this gives us VI transpose A transpose A times VI. Well, now Vi is an eigenvector for A transpose A. So this is equal to Vi transpose times lambda I times Vi. But remember, Vi is a vector in this orthonormal basis for Rn. So I can factor this lambda I out, and then Vi times its transpose should equal 1. And so this is equal to lambda I. So remember, we were talking about this idea that we wanted to, how should I say this? That we wanted to, well, remember we were talking about this idea that, with symmetric matrices, right, the length of the sort of amount that A would stretch or shrink a vector in a certain direction was determined by its eigenvalues. What we've just shown is that if we look at the unit eigenvectors for A transpose A, then the length of A times Vi squared is equal to this eigenvalue for A transpose A. But so this means that the length of A times Vi is equal to the square root of lambda I. And so this tells us a few things about this. First of all, the fact that A times Vi, which is some number squared, is equal to lambda I, tells us that lambda I must be positive. And since this was just an arbitrary eigenvalue of A transpose A, this tells us that, in fact, all of the eigenvalues of A transpose A must be positive. Or actually not positive, but non-negative. So all of the eigenvalues of A transpose A are non-negative. Therefore, we can order them in the following way, where we'll say lambda 1 is the largest eigenvalue, lambda 2 is next, and lambda n is the smallest eigenvalue, and we know they're all greater than or equal to 0. And again, that's because of this relation here, that lambda sub I is equal to this value squared. And so remember, now the length of this non-square, potentially non-diagonalizable matrix times this eigenvector of A transpose A is equal to the square root of lambda I. And the square root of lambda I is a singular value of A. I guess I should say these singular values. And you can kind of think of these as like almost eigenvalues, but they're definitely not eigenvalues. And so these singular values of A are these square roots of the eigenvalues of the matrix A transpose A. And we denote them as sigma sub I is equal to square root of lambda I for each of the lambda i's. And then much like the eigenvalues of A transpose A, we order the singular values, lambda 1 being the biggest first, or sorry, not lambda, sigma 1 being the biggest first, sigma 2, these aren't vectors, being the next one, all the way down to sigma n being the smallest. And as we have seen, the length of A times Vi is equal to sigma I, where Vi is a unit eigenvector corresponding to lambda sub I. And so this is a unit eigenvector, should be pointed out, for A transpose A. So we can study sort of how A affects the length of vectors, even for matrices which aren't diagonalizable, by studying the singular values of a matrix. So I just want to wrap this video up by finding the singular values of a matrix. In the next video, we will actually calculate the singular value decomposition of a matrix. So probably the easiest thing to remember is just that the singular values of a matrix are the square roots of the eigenvalues of A transpose times A. So this has a few parts. We're first going to find the singular values, and then we're going to verify that basically the lengths of A times the eigenvectors are preserved. And then we will talk a little more about some other things that we see, because this will sort of set up what we're going to do next video. So we want to find the singular values of A. And then, much like convention, we'll order them from largest to smallest. But so to do this, the first thing you want to do is calculate A transpose times A. Let me make sure I've got that right. Yep. Then you want to find the eigenvalues of A transpose times A. So the characteristic polynomial of this matrix would be 4 minus lambda times 13 minus lambda minus 36. And if you expand that out, you should get lambda squared minus 17 lambda plus 16, which, as we will see, conveniently factors to lambda minus 1 times lambda minus 16. And so we'll order these eigenvalues largest to smallest. So the eigenvalues of this matrix are 16 and 1. And this means the singular values of A are sigma 1 equals square root of 16 equals 4, and sigma 2 equals the square root of 1, which is 1. So finding these singular values of a matrix really, as a standalone problem, isn't horrible. As we'll see, the singular value decomposition tends to be a little more involved. But so next what we want to do is, what I'll do here, just to save time, I'll give you 2 unit eigenvectors for each of these eigenvalues, since it's not, the eigenvectors aren't really the part of this problem I'm concerned with. So V1, this is a unit eigenvector for lambda 1 is equal to 16. And so remember, this is an eigenvector for this matrix, right? Corresponding to lambda 1 equals 16. But what we're going to verify is that the length of A times V1 is equal to 4. So first, A times V1 is equal to 2, 3, 0, 2 times 1 over root 5, 2 over root 5. And so multiplying this out, you should get 2 plus 6, 8 over root 5. Is that right? Yep. 8 over root 5 plus, or not plus, but 4 over root 5. All right. So that means the length of this vector is equal to the square root of 8 over root 5 squared plus 4 over root 5 squared, which is equal to the square root of 64 plus 16 over 5. 64 plus 16 is 80, divided by 5 is 16. And sure enough, the length of A times this unit eigenvector V1 is equal to 4. So sure enough, sigma 1 actually does measure the length of this unit eigenvector. So we can actually do the same thing for the other one. So if the v2, and I think I've got the solution for that. So you can verify this on your own. It's basically the same calculation. I need the other eigenvector, though, for the third part of this example that I want to go over. So I'll just sort of note, if v2 is equal to negative 1 over root 5, 2 over root 5, and this is an eigenvector for lambda 2 is equal to 1, then you can verify that the length of A times V2 is actually equal to 1 as well. And it's the same process as what we just did here with sigma 1. So sure enough, the singular values actually do measure, again, how a matrix sort of stretches or shrinks vectors in a certain direction. But one thing I want to point out, and this will sort of hint how we're going to calculate the singular value decomposition moving forward. So we've already calculated A times V1 to be the vector. Where was it? 8 over root 5. 2 over root 5. A times V2, if we were to calculate this, should get 4 over root 5, 4 over root 5. Let me make sure that's correct. I think I'm missing a negative somewhere. Sorry. V2 should be equal to negative 2 over root 5, 1 over root 5. So V2, this is the correct eigenvalue for, or eigenvector for lambda 2 equals 1. And then A times V2, so actually the original eigenvector I'd written down was A times V2. A times V2 is equal to negative 1 over root 5. Or sorry, let me make sure. Yeah, negative 1 over root 5, 2 over root 5. So this should change to negative 2 over root 5, 1 over root 5. Yeah, so sorry about that. So this is the correct eigenvector for A transpose A corresponding to the eigenvalue 1. And so this would be the correct value of A times V2. And so what I want to notice here is that AV2 dot AV1, which is equal to 8 over root 5 times negative 1 over root 5 plus this should be a 4. There we go. Okay, now everything's correct. Plus 4 over root 5 times 2 over root 5 is equal to 0. So barring a few arithmetic mistakes, and I do apologize for that, this is the correct value of A times V1. This is the correct value of A times V2. Notice they're orthogonal. And so as we'll see in the beginning of next video, so this actually isn't a coincidence. So that wraps up video 1. So singular values of a matrix are the eigenvalues of A transpose A. What the singular values measure are the lengths of A times Vi, where these Vi are eigenvectors corresponding to the eigenvalues from which we derived the singular values of A transpose A. And so next video, we'll actually calculate a singular value decomposition of a matrix.